6-day faculty development program on emerging trends in sustainable manufacturing, advanced materials, and additive technologies. Today, we have a session speaker, Dr. Balasubramaniam Esaki, sir, Professor, Department of Mechanical Engineering from NITTR, Taramani, Chennai. Before starting our session, I would like to introduce our resource person, Dr. Balasubramaniam Esaki, sir, received PhD in the field of robotics and control at Concordia University, Canada. Is presently working as professor in Department of Mechanical Engineering and Dean for Center of International Affairs, NITTR, Chennai. He has published 3 books and more than 150 journals and international conference publication, and 7 patents have been granted under his credit. He received grants from various Government of Indian funding programs supported through Indian Space Research Organization, Defense Research and Development Organization, Department of Science and Technology, Science and Engineering Research Board, Department of Biotechnology, and other funding agencies. He has collaborated with Taiwan scientists under Indo-Taiwan Schema for development of micro-aerial flapping wings vehicle and formation control through image processing technique. During the Indo-Canada collaboration, his team deployed UAVs to inspect bridges and heritage structures across India and in Canada. In addition to that, Professor has had a collaborative work with South Korean Institute and industry under Indo-Coro funded projects to collect water samples and performed water quality monitoring in remote water bodies using novel ambitious UAV. His team deployed indigenous powder-based 3D printing system for defense applications in this project. His team have developed UAV for diverse applications, including power line inspection, telecom tower inspection and radiation measurement, bridge inspection, environmental monitoring, mining, infrastructure assessment, crop monitoring, precipitation spraying, surveillance and traffic monitoring, etc. His team has won first prize in national level competition organized by Power Grid Corporation Limited and the prestigious telecom sector Grants Bell Award in the category of Best Innovation Business Model. He has carried out consultancy project for diverse national agencies like DARC, Indira Gandhi Center of Atomic Research, Bharat Electrical Limited, ISRO, automobile sectors. His research interests are UAVs, robotics, 3D printing, non-linear control system, and sensor with online data acquisition systems. On behalf of Department of Mechanical Engineering, Welltech, Multitech, Dr. Rangarajan, Dr. Sakuntala Engineering College, I would like to give a warm welcome to Dr. Balasubramaniam sir to deliver his session on selective incubation sintering, low-cost powdered additive manufacturing. Thank you, sir, for your acceptation, and you can start your session, sir. Thank you so much, sir.
Thank you, Mr. Aravind. It is a nice introduction for me. So I would like to express my sincere thanks to Mr. Aravind for inviting me on this faculty development program and the Department of Mechanical Engineering and the entire team for organizing and inviting me. So I will share my screen. So hope it is visible, right?
Yes, sir. It is visible, sir.
Thank you. Okay, so good afternoon, one and all. This is a lunch time. How it is planned? Because 1 p.m. It is starting. What is
sir, Sir, we are practicing this for last 5 days, sir. We have informed the participants to finish their lunch by 12:30, sir. So sessions may start by 1 to 2 o'clock, sir.
Okay. So today is the last day.
Yes, sir. Last day, sir.
Okay. Great. So anybody talked about 3D printing in this last 5
Yes, sir. Yes, sir. We have had a couple of discussion about FDM, wire or additive manufacturing, sir, and some other basic concepts about 3D printing, sir. All the sessions are planned accordingly, sir.
Okay. So to all the sessions with reference to 3D printing.
Yes, sir.
Okay. So then I don't need to give any introduction to 3D printing. So this selective inhibition centering. How many of you already heard about it in this group? Any responses? How many of you heard about the selective inhibition centering? Okay, so this, sorry.
I think they will post in the chat box, sir.
Okay. So anybody already seen this topic, or anybody already studied any research article or any other reference you have made? Okay, so you are the only person, like, okay, Mr. Dharnish. Okay, so this particular process, this replacement, or maybe we can call it as low cost, because the selective laser centering, we are investing a lot of money for the lasers, and importing of lasers also becoming tedious and costly. So most of the times the lasers are being imported from abroad. So whenever you develop any system, or any laser based system, we are heavily dependent upon the importing aspect only. So to avoid that, and also to make a cost-effective way of one of the ways in which the powder-based additive manufacturing can work, that is the concept of selective inhibition centering. Okay, so that is a primary objective why this particular process. So this process was initially invented by Professor Koshnafis and his team from University of Southern California. They are from US. So how this particular process works is, for example, this is your powder bed. Okay, so in this powder bed.
Sir, sorry to intercept you, sir. Your screen is not visible, sir. You are in video mode, sir.
Oh, okay. Sorry. Okay, now it is visible.
Yes, sir. Yes, sir. It is visible,
Okay,
sir.
thank you. So this is the powder region. Okay, so in this powder region, we are having a specific shape. For example, a rectangular shape. If I want to print a rectangular shape, I will be inhibiting this periphery with the help of a solution called inhibitor. That is why it is called inhibition. So defining a part periphery with the help of an inhibitor. So we will see what are inhibitors and what are its functions later. First of all, I would like to introduce what is selective inhibition centering. So we are defining the part periphery or part profile by means of an inhibitor. So that is what the inhibition. And then the second step is we are doing the centering. Okay. So what do you mean by centering? Centering is nothing but joining of two powder particles. It is not melting. It is joining of two powder particles. So that is the basic difference between centering and melting. So when we apply temperature, maybe about 80 to 90% of melting point of that temperature, the powder particles are joined. So that is what called sintering. So that is why in the selective laser sintering, we are using lasers to hit the powder particles and they are able to join. Okay, similarly here we are able to join the powder particles. So that is why it is sintering. Okay, so we are selectively inhibiting and also sintering. That is why the name it is called selective inhibition sintering. Okay. So you can define this SIS. In short, we call it as SIS. It builds parts by sintering powder particles in the parts body and inhibiting the sintering of powder particles at the parts periphery. Okay. The parts periphery, that is the part profile, we are doing the inhibition. And in the region, we are whatever we are interested, where the sintering will happen. So we are completely replacing the laser systems with the help of basic heater systems. Either it can be infrared heater, ceramic heater, or what kind of thermal resources which are cost effective. Okay, so that resources will be mounted, and that will provide enough sintering temperature. Okay, so in a simple way, it looks like simple, but when you think about in a real aspect, the sintering and the uniform behavior of thermal behaviors. So everything will be a little tough, and the inhibition, defining the part periphery with reference to inhibition. So all those aspects were really challenging when we deal in a real time. So this project, whatever this particular process we executed for a DRDO project, and many PhD students were involved in developing this scratch from the system. Okay, so that was the aspect today. I'll be covering it. So hope you got what is selective inhibition centering. Do you have any questions now? You got the what is selective inhibition centering? Any responses? What is selective inhibition centering? Have you understood? Do you have any questions? Because once we are clear with this simple definition, then only we will move on. Okay. So at least one response. Thank you. Okay. So this is what we call, and we did some simple experiments before we actually we started our real work. So these are all some inhibition which we have done. Okay. And we also applied the heat sources. So you can see the burning here. So where we are able to see the centering of powders and inhibition behavior where the defined profile. So initially you can see the profile is not accurate because the inhibition is not proper. Okay, the inhibition was not good enough to make a proper profile. So this was the first and foremost simple experiment we started. So why we want to go for this SIS process? So we are avoiding the costly laser systems, and any indigenous polymer powders can be best utilized for sintering of this phenomena. Okay, so whatever the polymer powder particles, if you are able to make it, so we are able to do the testing and make the parts with the help of polypropylene, high density polyethylene or low density polyethylene, polycarbonate, polystyrene, whatever the polymer powders, the no sintering can happen with reference to the particular melting point before the melting, below the melting point. Okay, so here, as unlike the FDM, we don't have any support structure. Here, the support structure is not required. So we are able to remove the part from these surrounding materials easily. And this particular process are also we are able to achieve good accuracy, strength, and surface quality compared to other RP process, other AM processes. Okay, so this is a simple schematic, a working principle of the SIS. So as many of them understood about the SLS, similarly here also we have the chambers. One is a feed chamber, which is moving up, and another one is build chamber, which is moving down as per the layer thickness. Okay. For example, I want to deposit the first layer, and then I will move for 0.5 mm layer thickness. This is my layer thickness. Then I will move the feed chamber to 0.5 mm, and the powders, whatever it is coming up, that will be pushed here, and that is being deposited on the top of this build chamber. And then your second step is the inhibitor will come, and it will define the part profile. Okay, so based upon the G codes, we are able to do this inhibition deposition. Okay. So from inhibition, the part periphery is being defined. And the third step is the infrared heater or ceramic heater or other thermal resources what you are having as per your requirement with reference to the melting point of polymers, that will come into sintering, that is applying the heat sources, the parts, what the polymer powders are being joined. That is the third sequence. So in this sequence, you are able to make each layer by layer. So it will come down and it will come up. So each layer, while after printing, it will be stored and finally it will be removed from this build chamber. So the remaining powders are collected in this recycle chamber. So similar to the SLS systems. Okay, so only thing here we are using this inhibitor and some low cost heaters. Okay, so that is the basic difference between these SLS and SIS. So that is the fundamental working principles and what is in the SLS and what is available in the SIS. Okay, so this is the working. So we could realize this with reference to some robotic based systems. Okay, actually, this initial thought how we could use some robotic based deposition for precise delivery and some partition based motion for heating the layer by layer. And then we realized some basic understanding from the Cartesian type of motion, XYZ Cartesian type of motion. So these are all some basic conceptualization which we evolved during 2014-15, during the 2014-15. So finally, we were able to develop a complete system from the scratch. So this is the fabricated or completely indigenously developed system for our ADRDO project. So we have the control boards which will control XYZ and other extrusion motion. And there are some stepper motor and other extruder for extruding the inhibition and other aspects. Servo actuation for IR heater, limit switches are being placed, and there are some temperature measurement with some thermistors are being installed. So these are all some mechatronic systems, so mechanical and electronic systems which are indigenously made at our lab. So actually this work happened during my earlier tenure at Tech University, where we got this particular project, where Mr. Arvind also was working in Tech University, where we were colleagues during that time. And we actually, our JRF and other um, uh, MTech and PhD students were involved in developing this system from the scratch. So that is the system. So this is the system. So you can see the arrangements, how it looks like. We have got the feed and build platform. This is the simple stepper motor. And there is a power screw which is going to be rotating, and this bed will move up and down. Okay. And this is the powder deposition mechanism where we will have a blade and roller mechanism which is pushing onto it. And this is a simple infrared heater which will heat this uh, powder. I mean, the particular thermal resources are being applied. Okay, this is the infrared heater. And we have got the inhibition mechanism. This is a very simple mechanism, syringe-based mechanism, and it is being pushed with the help of a linear screw arrangement, and there will be a delivery through this nozzle. So the entire system is controlled using this control board. Okay. So here only every control actions from the G codes we are able to trigger, and the consequent motions for each feed and build platform or powder deposition or heater movement or inhibitor deposition. So all these aspects were being controlled. Okay. So this is our specification of our developed system. So every 3D printing, we need to define the specification. So our 3D printing system is capable with reference to 200 mm cube part build volume. Layer thickness minimum only 1 mm, because lesser than that, the penetration effect and other aspect, we were not able to do much because of the budget limitation. So our budget was not much to support to build a high-end system. It is average system. It is not a low-end system. It is not a high-end system. It is an average system which we develop. Okay, so the layer thickness is possible. Minimum is 1 mm, and the heater area of our heater, ceramic or infrared heater, which we used for many heater types, and the print feed rate, that is inhibition feed rate, is 1 to 3 mm per second, and we can hold up to 100 ml inhibited liquid. Okay, so powder feed rate, heater feed rate, nozzle diameter is 0.4 mm. Okay, so these are all some specifications which we arrived at of our SAS system. So we have used these two softwares. One is Slice 3R for tessellation. Everyone knows about, we need to do the tessellation, that is the STL conversion and slicing the layers, right? So that open source software Slice 3R we have used, and then we need to control the entire system with the help of the Pronter Phase system software, where inhibition and heater and bed axis and powder feeder, all these motions are being controlled using this software. So we have used these two softwares for our purpose. Okay. So this is a simple schematic how your basic working model. So we'll have a CAD model, and then we will slice through Slice 3R, and then we need to give access to the Frontier phase for other heater and ink deposition and other motion of beds. Okay, so that input is given to the hardware, and initially polymer powders are being laid out, and then inhibitor is deposited according to the profile, and then heater is moving on top of this particular layer. Okay, so this is a simple video which you can see how it works. So initially the powder layers were deposited. Now the inhibitor, so you can see a syringe, simple syringe, and it is now delivering the inhibitor. Okay, so it is a very cost-effective process. We have used whatever available at low cost. So now this inhibitor has defined the part periphery, and the second motion, as I mentioned, the heater will come into play. You can see now the heater is not switched on now. It is automatically switched on when it is reaching towards that particular region. Okay, unnecessarily we don't want to waste the energy and not to sinter the particles. So we are making the G codes in such a way that it is according to the required place it is switching on. So here also a simple linear screw and stepper motor arrangements to make the proper small, incremental motion and controlled motion. Okay, so that the uniform distribution of the heat, that is very, very important for centering. So you can see there are some powder particles are burning out. I mean, the smoke is also coming out. Okay, so this is the reverse motion. Even in the reverse motion, you can switch on the particular the heater. That is also can be done. So there is a first layer which you can see it is being sintered. Okay, so now the bed will move and deposit the powder. So that is what the second layer, which will lay down the powder. Okay, so once it is laid on top of it, now the inhibitor will come into deliver this liquid to define the required periphery of the part. Okay, so then after that, the heater will sinter the powder particles. So this is a sequence in which the layer by layer, the particular parts are being sintered. The powder particles are being sintered. Okay, So how this is how one can understand that basic working model. Okay, these are all very crude models. This is not complete model. These are all the basic educational models. Okay, so whenever you develop any system in your institute or in your lab, you may have to use this kind of basic setups. You may not be able to buy high-end systems or high-end sensors. Okay, so you can use simple servo motors, simple screw mechanisms, simple boards, right? So that will give some idea how it works and how to control. Okay, so whether we are able to do proper motions. So that is the work which you can think of. So you can understand now this is being sintered. So see now the powder is actually joined. This is a simple example how the powder is being joined. Okay, so like that. So there are some issues like burning issues. So then we need to have a controlled environment and controlled temperature. So that is what we need to have. So this is the open atmosphere we did it. So if it is into control environment and control atmosphere, and these problems will not occur. So this is another way how we are able to uh, get the G codes. That is the software using slice 3R. First, we are using the slice 3R to slice this parts. Okay, so now we are slicing, and that particular G codes. So this is a G code generated, and that is being exported. Okay, so then that exported code we are sending to this frontier phase. This software is frontier phase. So now the frontier phase and the hardware is being connected. Okay, so from here the information, whatever the G codes, it is being sent to this controller, and then it is being triggered. So that is the triggering more aspect, how this motion of the inhibition. Okay, so without having all the powders, we just want to showcase how it works. Okay, so we have also got some limit switches, these two ends. Okay, and we are having this bend moment. You can see a small up down movement very closely. So this is synchronized. So that is based upon the layer thickness. What is the layer? According to the layer thickness, the bed motion will be controlled. Okay. So these are all some observations which you can understand. So what I'm trying to say here is this is a completely from the scratch, low cost additive manufacturing system. Okay, so whatever the investment which we had, it is very low cost, and then we are able to make a simple new kind of system using this basic motions. Okay, so this is how the system works. Okay, so this is a heater movement, how the heater is moving slowly. Okay, so once it is turned on, and it will be delivering this thermal radiation on top of this powders, and that will be centering the powder particles. Okay. So this is a simple example how we have demonstrated. So till now, you have got any questions? Is it clear, the working principle and the functioning of SAS system?
Clear,
Yes,
sir.
sir. Fine,
Clear.
sir. Hello, sir. Sir, actually, that you have talked about the heat effect, so near to that particle.
Mm.
So, what are the means? Uh, do you have any plan to reduce it? I think because we are focusing on the periphery of the shape or kind of design, but it is affecting nearby material. So I think it is not good. And also you have mentioned, you have not mentioned about the nozzle material. I mean temperature ranges. I think these are the some was missing in your I think the tables. If you know about it, if you remember that, please let me know. I mean, if you know about it, please share it here, sir, because it will be helpful for designing as actually nozzle
Okay,
material.
so our nozzle diameter for inhibition was 0.4 mm.
0.4 as a nozzle material, sir.
Nozzle material standard, because this is a liquid only we are delivering, so standard poly material only we have used. Whatever the conventional polymer based nozzles which are available for FDM, that is also that is was only used.
Okay, so the temperature ranges, sir. How?
And this temperature, what it could do, the ceramic infrared heater up to maybe 300 degrees C max for
So,
polymer powders, it's having melting point about 200 or 250 degrees C. So we need almost around 80 to 90% of melting point. So we may need around 200 or 180 degrees C melting, the sintering temperature. So we are able to manage the ceramic infrared heater for that particular melting point materials.
okay. So
And
do
then
we get?
you are asking about the other regions which is being exposed. Yes, it is a good question. That is what actually we have to do masking. Okay, so masking will do only with reference to the particular place where in which we want to apply the heat sources. Other places can be covered with some other, cover can be done. That is, we have not done, but we have made only switch on and switch off in the desired region. So that is what we did it.
Okay. So one more thing, sir, regarding that interfacial bonding between the particles, or how was the strength or the? Have you tested the components, sir? Whether it is
Yeah,
sustaining
it is coming to the
body?
next. I'll come to second phase. I'll show some mechanical and the tensile, compressive, fatigue, and other test which we have done, and the results I will show now.
Okay, so I want. I'm interesting to know about the failures. I mean, how it was occurred, how it is giving results actually.
Yeah, next I will explain. Another
Okay, okay, sir. Waiting,
few
sir.
minutes I will explain that one only.
Okay, okay, sir. Thank you, sir. Thank you, sir.
Any other questions? Okay, so due to the shortage of time, I'll just quickly go through. So initially what we did, we want to understand the thermal structural behavior. Okay, so we want to understand which polymers and, for example, low temperature, high temperature application, if we want to define some polymers. So we have selected some polymers which are like polypropylene, polycarbonate, polystyrene, ABS, HDPE, and LDPE also. These are all some polymers which are maybe below some range of 300 degrees C. That particular polymers we considered as one group, and we have done some thermostructural analysis. So you can understand from this picture, this is the powder region, white color, and this region is the inhibition region. So we have applied the thermal loads with reference to the time steps. That is what the transient analysis. With reference to that, we have got the thermal temperature distribution that is given to the thermal analysis. So that is the structural analysis. So thermostructural analysis. So with reference to that, how the thermal stresses and thermal strains were induced. So you can understand the thermal stresses and thermal strains and the displacement, okay, and the temperature profile. So among these polymers, ABS and HDB obtain minimal displacement. Okay, so that is the conclusion number one. And we did some thermogravity, gravimetric analysis and differential scanning calorimetric analysis to understand the melting point. Okay, so and the residual mass presence after doing the sintering. So after doing the sintering, about 93.87 percentage mass is remain during this particular process. So we want to work with reference to the around 200 degrees C, because our temperature, our say he was was asking about the temperature range the heater can handle up to 300 degrees. So we want to have almost 200-degree range particles we want to understand, and HDP, of course, it was given a minimal displacement. That factor, we have selected the HDPE for our further work. So these are all some particles shapes and the sizes. So HTB in the range of 35 to 80 micron, and these are all weak material, PTFE and polystyrene. So you can understand from the HTB they are uniform, and everyone knows about the particle shape should be spherical. So almost they are into spherical shape. So that is the first and foremost thing which we attracted the HTB. So that is about selection of polymers. So what polymer we want to select for our work, that was decided based upon the finite element analysis and the particle size and shapes. And second aspect is selection of inhibitor. So what is inhibitor? Inhibitor is nothing but which is being defining the part periphery, and it should be dissolved in the. It should be also dissolved in the water so that the post processing can be avoided. So that is why the Professor Koshnavish and team selected the salt materials. Okay, they have cleverly selected that all the salt materials, once after 3D printed parts, just if you are putting into water, that will be dissolved. So they are very clever in selecting the potassium iodide or barium chloride or magnesium sulfate or sodium sulfate, whatever the material which are dissolving into the water. So that is number one. And number two is it should have a high melting point, because once we have the heater, I mean, it is heating up to 300 degrees C, it should not melt that inhibitor. So it at least it should have a three times greater melting point, higher melting point. So salt will have a melting point about, for example, here it is 681 degrees C, here it is 962 degrees C. So imagine that your heater is having 300 degrees C, it will be not melting. Okay, so that is why we need to select the high melting point material and soluble in the water. So this is the primary aspect of selecting the inhibition material as salt. Okay. So for 100 ml of water, what is the content for A, that is potassium iodide, and we have also introduced isopropyl alcohol that will control the dispersion of the solid, the liquid into this polymer powder. Okay, this isopropyl alcohol will reduce the dispersion effect. Okay, so we need to optimally look into it. So there was a big quantum of work which was involved to finalize this all these combinations. So we did so many experiments. So finally, we understood that K was performed better than other aspect. Okay, so that is the conclusion from the Professor Koshnavish team also. So similarly, we have done the penetration as per the inhibition dispersion. So we have controlled the dispersion with reference to an accuracy about 2 mm. Okay, so this is the final accurate part with reference to the inhibition of that particular inhibitor. Okay, so then we did the sintering phenomena with various heat resources and various polymer powders. So HTV coarse particles provided a good sintering. Still it is burning, but still we can control this. But other powder particles are not proper, and they are not able to do the justice in the open atmosphere. So this is controlled in the open atmosphere. Somebody was asking the nozzle. Okay, here is the nozzle which we have used for our work. Okay, so red, blue, and other nozzles. So um, these are all some nozzle types which you can think of. And then we have measured the width of the particular inhibition. That is what I said, the dispersion, how much it is being dispersed in this region. Okay, so this is the dispersion which was due to the isopropyl alcohol, control of isopropyl alcohol. So the inhibitor, how much it is being dispersed. So this is the simple measurement after sintering and inhibition. So we have got error about 2.81 mm in the width and 2.84 mm in the length side. So this is the problem with reference to the dimensional accuracy. So how are we going to reduce it? So that was the challenge which we have we would like to address during our course of experiments. Okay, so that is what we decided to do, more experiments and more trials. And this is a first level understanding of little complex profiles, whether the inhibition is proper or not. So this is the little complex profile, and the inhibition is uniform. And then we did some gear profiles, and that is also in a controlled. So we are able to do more iterations and more trials and more improvements with reference to control of the inhibition. Okay, the periphery, defining the part periphery. So that is the observation here, which I would like to highlight. So finally, we have selected this combination. Potassium iodide is 138 gram for 100 ml of water. Okay, among these inhibitors, this is being selected. So based upon these two studies, after selection of polymers, that is HTPE, high density polyethylene, and then potassium iodide as an inhibitor, we started doing the sintering of the powder particles with some heat energy. Okay, so varying the heat energy from 75 to 90 percentage of melting point. Okay, so starting from 75 percentage to this is 90 percentage. Okay. So that is what we did it, and then we understood the SEM images also. You can understand from 75 percentage it is not joining, and it is joining. It is slightly joining, and it is almost joined here. Okay, it means around 85 percentage, 85 percentage of melting point of the material. The sintering phenomenon is better. So that is the observation here in this image. And some of them are asking about the strength characteristics. Yes, we did tensile, which was achieved about 26.95 megapascal. So again, we varied the different sintering temperatures, 75 to 90 percentage. And then these are all some SEM images. So still there are some voids because it is open to atmosphere, and there are so many other atmospheric reactions. Since we don't have control environment, if you do the control environment, this also could be avoided. So due to the budget and other limitations, we are not able to make a control environment. And this is the flexural strength, which we achieved about 31.3 megapascal. And these are all some understanding. And we also did some surface roughness measurements. Okay, so these are all some basic studies which we have initially did it. Okay, so first and foremost thing, we have done some basic studies without having any control of the process parameters. Okay, if you look into SIS process for each aspect, for example, powder compacting, inhibition, or centering, or inhibition, printing and penetrating, you have got many process parameters. This many process parameters. Okay, so which process parameter and how does it influence the part quality and part strength? That is the research works where around 4 PhD students worked in a different aspect. Okay. So as per the literature from the Professor Bhushanafis and team and our understanding, these are all the main factors, main process parameters: layer thickness, heat energy, heat to feed rate, and printer feed rate are heavily affecting compared to other process parameters, which we also understood from our experiments. And from the Professor Bhushanafis also did all these process parameters. Okay, so based upon that, we have selected different set of part quality characteristics and strength characteristics. For example, mechanical strength characteristics, wear characteristics, dynamic mechanical characteristics. Okay, so all these specimens as per the ASTM standards were 3D printed as per the required aspect. So we have done the RSM Bose-Benton design of experiments, and then for each experiments, for example, dimensional accuracy or mechanical strength. So we have fabricated the number of specimens, and then we did the analysis of variance, and we also used various optimization algorithms to optimize the process parameters. And we also done some intelligent modeling using fuzzy logic and AI and artificial neural network. So actually, this flow chart will give you a broader spectrum. So each, for example, dimensional accuracy is on mechanical strength maybe one PhD thesis, and dynamic mechanical analysis and wear rate maybe another PhD series, and fatigue another aspect another PhD thesis. So different with reference to optimization algorithm and intelligent modeling. So different aspects we have no given the PhD students to work across this development of all these understanding of these characteristics. Okay, so that in a quick way, so we did the RSM and then ANOVA. So from the ANOVA, we would understand the influence of process parameters and we formulate regression equations. Intelligent modeling, we are able to compare the experimental results with the fuzzy logic, and using optimization algorithm, we are able to find out the optimal process parameters. Okay, so this is a framework in which the entire methodology. So these are some RSM BBD design of experiments, and this is the ANOVA table, which is providing what are the most influential process parameters. In the case here, it is D, and the coupling parameters A and C. Okay, so what is A and what is C is being defined here. So A is layer thickness, C is heater feed rate, D is printer feed rate. Okay, so that is what here you could see this influencing process parameters, and you can understand the response surfaces based upon that, which one are affecting with reference to the variables and their influencing of these linkages. Okay, so the conclusion from one here is build layer thickness 1 mm and heat energy 27.8 joule per mm squared, feed rate of heater about 3.39 mm per second, and printer feed rate about 120 mm per minute. We are able to get at least a good level of dimensional accuracy. Okay. So we also did some fuzzy logic based intelligent modeling. So our input and output based upon the previous box prints and design, we have evaluated this two informations. Based upon that, we have designed this membership functions. Okay, and fuzzy rules are being formulated based upon the number of experiments which we have done, 29 number of experiments in the box prints and design. So based upon that, they made the fuzzy rules, and then that fuzzy logic provided at least equal to the experimental value. So you can understand from here that experimental value provided 2.66, 1.21, and zero point 0.6 mm, and fuzzy logic also provided nearest to that particular measure, 2.78 and 1.27 and 0.65 mm. So what it conveys here, we can do the fuzzy based algorithm instead of doing the experiment in a critical times. Okay, so if you can believe the fuzzy logic also when we want to evaluate the performance characteristics. And we have done some optimization of the process parameters using genetic algorithm MATLAB toolbox. Okay, so here we are able to converge, and the convergence provided the process parameters. These are all your A, B, C, and D parameters. Okay, so this is what the first level understanding of the SIS process. How we have done some RSM, response surface methodology, and then with the our design of experiments, and then with reference to the intelligent modeling and optimization algorithm. Okay, so as per this genetic algorithm, our optimized process parameters are defined here. Okay, so that is what the first level understanding for the optimization of the process parameters. Okay. So similarly, we have done for other aspect like mechanical, tensile, flexural. Okay. So then fuzzy logic, fuzzy rules were formulated. Simulated annealing were used here, and based upon that, we have obtained the results. And for the tensile strength and the flexural strength, what could be the process parameters? And then we have done the wear rate. So this is the RSM and fuzzy logic. So it was like a parallel work between different PhD students. I'm just conveying in a very short time. So we have used here desirability approach, and then we have investigated with reference to surface roughness and same aspect. And then we have used here gray relation analysis algorithm. Okay, so then we did some AFM measurements to measure the surface quality based upon the surface roughness, optimal process parameters, printed process parameters. Okay, and then we have done some analysis for understanding the vibration characteristics, dynamic mechanical properties, and these are all some observation for loss modulus. Loss modulus nothing but energy dissipated as a heat, and storage modulus is energy stored during the application. Okay, so this is the important profile for the vibration aspect. So again, we have done the RSM ANOVA, and here we have used ANN, artificial neural network, for modeling the system. Okay. So again, we have done the experimental results which are compared to the ANN. So based upon this inferences, okay, so this is an important table. So after doing all these understanding, for example, you want to set the process parameters, optimal process parameters to achieve a good dimensional accuracy, okay, according to our results and according to our system. Okay, so you need to set these process parameters. And then if you run the system, your dimensional accuracy is better. Okay, I would not say it is completely accurate. It is better. Okay, it is a very crude model of which we have done the experiments and evaluated the system performance. Okay, still it is not mature. Okay, because it's the first and foremost prototype model. So similarly, if you can do tensile, flexural, wear, and surface roughness characteristics, so whatever your process, what you want to achieve, we have to maintain these process parameters for our system. So that is the point here. Okay, how are we going to optimize and how are we going to achieve this process variables? So these are all some fabricated parts, since it was actually for the defense application. So we did some basic parts. So these are all the 3D printed parts from the system. They have obtained a good strength. So it is a very crude model. And some of the PhD student, one of the PhD student also did fatigue analysis, and then he tested to replace the brackets. So this is the bracket. Okay, so this bracket again 3D printed with our system being replaced here. Okay, and it went for some cyclic loading. So similarly, when you are doing some real-time testing with your 3D printed part to replace the existing part, then you can understand the functional aspect of the particular part and the strength characteristics of the part. Okay, so this is some of the basic level test which our earlier Whale Tech University and IC Engine Lab, which we did it. So whatever I mentioned as polymer-based SIS process, now Professor Koshnavich's team is developing metal-based SIS process. Okay, so it is a very promising to go for metal, but it will be very tough to do that. So if you can understand the approach, SLS, 3D, FDM, it will be bulk sintering. SIS, it will without use of the printers, but it is bulk sintering. Okay, so that is what we want to have some compromise. What kind of printing technology for bulk sintering, which you can think of, then it will be only for SIS process. Okay, so these are all some printed parts from Professor Koshnavis and team. printed parts. Okay, so this is our system. So when we worked during that time, there was so much of powders, and there was so much of efforts which our JRFs and other PhD students, and it was very complicated when we started our system from the scratch. So whatever you see the system, everything is designed indigenously and fabricated made here inside our campus only. Some of the parts only we have given outside for final finishing and other aspect. Mostly we have used our in-house facilities, which was available at Painting. Okay, so this is the complete setup where we did our all the experiments. So this is the frontier phase software and some of the VR test and some small microscopes to understand, and whatever the relevant aspects which are you can see in this particular picture. Okay, so because of time, I want to complete it in 1 hour. So I just finished it because of the time Mr. Aravind has given to me. So the SAS process, which is a new process, this is not actually matured in India. So very few people actually worked, and from our end, we are the first in India to develop this system in DRDO project. Okay, so still the system is not explored in India. Okay, so if you want to jump in, you can jump in, but you have to be very cautious on doing this particular part of this product development side. Okay. So that is from my end. Do you have any questions from anyone?
Hello, sir. Good afternoon, sir. This is Dr. Arun speaking here, sir.
Yes, sir.
Sir, actually, it was a really wonderful presentation, and you have made a, wonderful machine to make 3D printing in additive manufacturing, we can say.
Thank you.
So, okay. So, coming to that part size, sir. Suppose if in case of the part size is bigger, printing part size is bigger, and if it is a smaller, is there any differences you have observed in dimensional accuracy or strength point of view? I just want to know that.
Uh, Actually, we have not compared. Actually, this project was completed in 2016 itself.
Oh, okay.
Very old project. I didn't remember till what we made any small part comparison. But whatever we made the particular size, we were able to print. Actually, you can see some parts, whatever I was showing. Yeah, so these are all some parts. You can see this cylinder and
Uh,
this shape, and this is some profile. So I think there was no problem for according to me. The parts were able to print it.
okay, sir. Because if
Yeah.
it is in the smaller case, then there will be a chance for a good dimension accuracy. Some cases, in
Yes,
some other
of
cases,
course.
if we are increasing the part size, there will be a variation in dimensional accuracy, like the surface roughness. I think one of your research scholar result was around 10 micrometer in surface roughness. I think RXY is that more than
Mm.
10. So I
Mm.
think